Make sure you grab these on the way out.
Yes, ma'am.
Okay, so everybody got an extra 4 points, and I try and do that on each exam to make up for what I hope are not grading inequities or goose in the grading. So, because of that, was there a bonus on this? I don't even remember. No. Okay, so because of that, there was the possibility of getting in excess of 100%, and there were a couple people, at least I think, who did this. So, just to kind of let you guys know. On each problem, I should have indicated how many points I took off. I would then circle the number of points you got on that problem. On the solutions to the exam that I handed out, number of points per problem is listed on there. The one goof I had I did not notice is that problem 4, here, in problem 4, for some reason, as I was setting up the number of points, I set for A and B up to be worth 6 points, and then for C, which should have been a separate problem, was set up also to be 6 points. So it'll, you know, if that causes confusion, then see me. I would strongly encourage you to make sure I added up the points on each page correctly, and that I added up all the points on the exam correctly. Periodically, I screw up. So if it were the final, I would be double and triple checking every time I do this, but I figure during the regular semester, it's in your guys' interest if I let you guys do the double checking. Okay. Solutions are on here. Some of these problems, especially on this first page, come with a variety of possible answers. So, you know, your answer may not look exactly like mine. I don't really recall anything being blatantly a problem. Yeah, I don't know. So I would encourage you to see me if you have questions. Remember that I grade on a 10-point scale. So 90 to 100 is an A, 80 to 89 is a B, etc. Okay, I guarantee that much. Sometimes I slide a little bit below. What was the other thing I was going to say? Oh, this material is steadily used all throughout the remaining chapters, with partly the exception being chapter 13 that we're in now, I think. We're 13, are we not? Yeah. So just about everything that sits in this is going to be used. Melissa. Just about everything's going to be used. There is no way you're going to get through this course if you can't do the basic skills that are on here. So because of that, I feel fairly comfortable in saying that by the end of the semester, I will know, short semester though it's going to be, I will know that you know stuff. I've had people fail first exams but get an A in the course off of me.
Wow.
And for that to happen, there's got to be a change in terms of whatever's making the trouble for you. And I'm usually pretty good if you show me your test going through, okay? Now, I have no idea if they're going to do anything to make up this extra time. I know that they are not taking away spring break. Probably 95% of me says yes, I don't want them to do that, but academically for this class, it's a problem. This class is already crammed way too tight, even if we were meeting every day of the week. You remove 2 weeks, and I have no idea how we're going to get through the material that we have to go through. I am going to skip a few things and cover other material lightly. And I'll let you know that as that comes. So, I know that I've got to go back and at least give you guys somewhat of a review of where we were, because it's been a while, I assume, since we've had a chance to look at this stuff. But fair warning, we're just not going to have any slack time. Exams that we do, I'm going to put them in the testing center. Okay? If you're not at all here during the day and that poses problems for you, see me and we'll make some sort of arrangements.
So the rest of the exams will be taken in the testing center?
Yeah,
Okay.
I don't know of any other way to be able to deal. That at least will give us a few more hours.
We have 3 exams and then the finals that we have
Well,
left.
right now,
Yeah.
I have no idea. If I had my druthers, they would ditch finals week and just say do the regular schedule, which would give us 2 more meetings, and then we test on the last day, but I'd have, So I don't know.
I don't see how they're not going to be able to extend, because the entire campus will shut down for 2 weeks.
Yeah, it's funny, my Monday, Wednesday classes, they lost a week, but the Tuesday, Thursdays.
Is that something that they could do, just make the semester a week longer?
I don't see why not.
Yeah.
Normal schools do it.
Right.
If you have 14 snow days, you just go until you're done.
Yeah,
It's
but that's public school, and this is.
well, we paid for this. I would rather have these classes than those.
That makes
if you want,
if you want,
I'm willing to walk around with you and get something
Yeah, but
signed by the majority of the
it's not
school who
gonna
wants
be-
to stay.
But those that have census leave
Okay.
the week.
Yeah, there's
After.
There's all
things.
kinds of other conflicts that
Yeah.
come into play, and I don't even know how much of that is in control of this school. It may be entirely in control of
Right.
Tennessee Board of Regents that governs everything. So I don't know. I have
And
no
then we were
idea.
discussing what is possibly going to happen Wednesday night with more
Oh, yeah.
icy rain.
We're probably gonna cancel them too. Okay, so, let me go back to where we were with the vector value functions. So, and some of this was on the exam. So, I haven't written anything. I scribbled something. Okay, so vector value function are functions like RT equals t squared. That's in 2 dimensions. They may equally well be in 3. You can write these with ij or ijk, etc. Okay? They trace out a path which could be in 2 dimensions or it could be in 3 dimensions, and that path has got a direction of motion associated with it. And the way in which we understand the function's relation to this path, I'm doing this in 2 dimensions at a given point, I would look at R of t, and if I sketch that vector by putting its tail at the origin in standard position, and then its head will come and superimpose on the point in the path. Okay? So, in other words, this basically gives me a parameterization of the path where the x-coordinate is corresponding to the I component and the y-coordinates corresponding to the j component. And if we're in 3 dimensions, then my z component would be the k guy here. Okay? If we look at this and then play games with drawing in difference quotients, we end up seeing that R prime is tangential to the curve and points in the direction of motion. So in this case here, at least would be a correct drawing of the direction of R prime. It's tangential and follows the direction of motion. Okay? Questions here?
It's not necessarily perpendicular to?
Not at all. So if I look at other places, let me see. Suppose we look here. This would be my R of t, and R prime would look like this. And so, sitting by itself, I have no indication as to what the angle is here. There will be specific instances where R and R prime are orthogonal. If you look at motion around a circle centered at the origin, then your R looks like this, and your R prime looks like this, and you can parameterize your circle and actually compute R and R prime, and you will see that you dot them, you get 0. So, that's pretty easy to do. R of t would be, say, k sine or cosine of t, k sine of t, k would be the magnitude of that vector, and R prime would be minus k sine of t and k cosine of t. And you can see in this example that R dotted with R prime is 0. And this extends up into 3 dimensions or even higher if you are looking at any path along a sphere centered at the origin. Then you look at the R and you look at the R prime, and they also will be orthogonal to each other. And we may or may not end up justifying that. But my point is, it's easy enough to compute here. The thing is, you go around a circle, there's only so many ways you can do that. I mean, you can speed up and stuff, but, you know, you're going to parameterize it like this. If you're looking on the surface of a sphere, there's all kinds of possible paths through any given point. And so it takes a little bit more effort to show that R and R prime, in this instance, are also going to be orthogonal. But we need to do a little bit more work before we get up there. But it does extend. So in general, R dotted with R prime may be positive, may be negative, may be 0. Okay? All right, so let me see. This was sitting in here, and there was a problem on the test. I mean, we can integrate R of t, we get back a vector, and we can differentiate R of t, and we get back yet another vector. So, you know, they ran through this in the first couple sections in the chapter, and that's where the test basically stopped. So, in section 13.3, not a whole lot that you have to worry about. The primary thing there is the formula for arc length, which you saw a version of in Calc3. So if you have a function y equals f of x, and you want to know the distance that you travel along that curve, then you got a nice formula. S is equal to the integral over that interval a to b, square root of 1 plus, and then you take the derivative of f and square it, and you get this formula out. And this is generated basically from mean value theorem, but basically it's generated by doing the typical approximations that all application integrals seem to come from. You do a whole bunch of straight line estimates to that distance, and then the mean value theorem kind of translates it into the appropriate Riemann integral, and you get this result out. And you may or may not remember it in Calc3, primarily because these integrals, where you have square roots of 1 plus something squared, are nasty integrals, even with tables. And so unless these problems are cooked up tremendously, you're not able to basically do anything other than estimate numerically. Okay, if I parameterize this curve, I would parameterize it by letting x equal t and y be f of t. And the derivative of t is 1 plus, and then I have the derivative of the y component squared. Well, the problem with this type of formula is it's only being applied to functions. But it can be generalized, and if this was the parameterization what you get is a specific example of the more generalized form. So if I have an R, which is given by x of t, y of t, I can do this in 3 dimensions. The extension is obvious. So this gives me some curve, and if I'm at this point in the curve at a specific time, say time A, I run through this curve, and suppose I'm here at time t equals b. And if I want to know how far I've traveled, this formula that you see in Calc 2 gets generalized. That arc length ends up being the integral from A to B, square root x prime of t squared plus y prime of t squared dt. And again, if you look at what we wrote down for the Calc 2 version, and if I parameterize that curve, t, f of t, you see that applying this formula gives you this exactly. Derivative of t is 1, derivative of f is derivative of f. Okay? And if I had gone out to 3 dimensions with the z of t here, you just would add plus z prime of t, the quantity squared. These integrals are equally obnoxious. I mean, if anything, they're worse to compute with, but it's going to be part of other problems that we need this for, and the computations in those cases will not be as obnoxious. The one thing that you should see is that this square root of x prime squared plus y prime squared is the magnitude of not r, but r prime. You know, so your r prime is x prime, y prime, and if I said what's the magnitude of r prime, it would be square root of x prime squared plus y prime squared, which is exactly what I have here. You get this formula out. It's the same formula as up above. It's just writing it in a slightly different way. And this would tell me that s prime of t would be magnitude of r prime. And it would also tell me that the differential of s is going to be magnitude of r prime dt. These are not things we will see used a lot right now, but we will see it coming into play. Okay, just be a while. The reason they're bringing this up right now is their discussion of curvature. So, we talked briefly about what do you want curvature to do. And in some cases, it should be clear that however one comes up with a way of measuring curvature, the curvature of a straight line should be 0. And the curvature as you move at different points around the circle should be constant. The bigger the radius of the circle, the curvature should be smaller. The smaller the radius, the tighter your circle, curvature should be bigger. So the curvature of a circle is tied to its radius. And as the radius increases, you would expect curvature to go down, and vice versa. So these were things we talked about, and there are different ways one can define curvature. The way in which we defined it was, well, seeing how much change you were to get in the direction of R prime. So that where you've got a lot of curviness, your R prime, as you come around here, is gonna change a fair amount. But where your curve levels off, you look at different points, you wouldn't expect to see that big of a difference in R prime. Well, the only problem with just looking at the derivative or the rate of change of R prime is that if I have a curve like this, and if this is my R prime at this point, and at this point, this is my R prime, well, R prime has exhibited a fairly substantial change. The change is entirely in its magnitude. Well, not entirely, but the significant change is in magnitude, not so much of a change in direction. And that becomes an issue because I can't just measure the rate of change in R prime because it's gonna maybe mislead me to think curvature is big where in fact it's not. The other issue is, given one parameterization, I might be passing through this point pretty quickly. I can have high speed, but maybe a different parameterization has me going through this point slowly. And curvature should not depend on either of those two possibilities. Okay? So when we work with our definition of curvature, we want something that will give me a measurement that only measures the rate of change in the direction of, that will only measure the rate of change in the direction R prime, not in the magnitude of R prime. And I also want independence of parameterization. So the way this is done is technical. They institute a common parameterization for which every time you go to measure curvature, you use that given parameterization. The only problem is it's a real obnoxious thing to work with. It's what the book will call the arc length parameterization. They run through some sticky, messy exercises. Basically, if you did them, they would convince you real fast you don't want to do them. If we had time, which we didn't have it before, we certainly don't have it now, I'd run through it with you, but I don't think it's necessary to go through. It is necessarily part of the definition to avoid these issues that I'm talking about here. But because of the difficulty in computing it, we don't mess with it, okay? And so manipulation is done to get the formula into such a way that it's easy to compute, okay? So this first issue is dealt with, the issue of what happens if r prime is changing its magnitude rapidly, not necessarily its direction. That issue is dealt with by defining what's called the unit tangential vector. So T for tangential is defined to be r prime of t, that's the vector that's in the tangential direction, and if I want to make it unit, I
But the magnitude.
divide by magnitude. So this is one of those places that underscore why we did all the exercises with find the unit vector in a direction. Okay. Later on, there'll be a problem where we need a vector in a certain direction, but I need its magnitude to be something. So, we'll make use of all of that. But what this is going to do is change this picture, because it's not going to be the rate of change of r prime, it's going to be the rate of change in t. And the reason is, this is entirely going to measure, when I differentiate this, rates of change in the direction. Because every one of these vectors has length 1, so there's no way it's going to measure anything else other than rates of change in direction. Okay? The other issue is the issue of parameterizations, and that gets taken care of by simply everybody using exactly the same parameterization so that everything is being done uniformly. Okay. So what do? We define, S is that arc length, and you don't need to worry about this, but this is the arc length parameterization. And curvature is defined, it's usually given a kappa, the Greek letter. And it is defined to be the magnitude of the derivative of this unit tangential direction. When we're looking at this with a parameterization that we never really will work with, but that's the formal definition. And it makes sense from a geometric standpoint, but like things that we've already looked at, dot products being one of them, the geometry definition makes sense but can be very difficult to compute. And so we get a much easier version of this